So continuity on a closed interval. And we say it is continuous on the closed interval a to b. If it's continuous in between a and b, which you saw in that video, meaning you can draw it without lifting your pencil from a to b. And at a, you would have to go from the right-hand side. Here's the next picture. Okay? So this example that we're going to do here, this would be continuous on its interval because at the left side point, as you approach it from the right side, you get to the point. And the right side, as you approach it from the left side, you get to that point. So basically, if you draw the function and the endpoints of that function are included, it's going to be continuous on that closed interval. That's the intuitive part of it. The mathematical part of it says it has to be continuous at every point in between, and it has to be from the left side, as you approach that left point from the right, you would hit that point, and on the right side, as you approach that from the left, it would equal to that point. So, we're going to sketch this graph. It's already been sketched there for us. Okay, square root of 9 minus x squared. And prove that it's continuous. So first of all, we have a domain that goes from -3 to 3. For any number in that domain. So what we're going to do for a proof here, and this is where he was saying in the video that we just watched, if you have the actual equation, you can do a formal proof. This is what the formal proof set looks like. You pick some random number between -3 and 3, and you call it c. Okay? The limit as x goes to c of f of x would be the limit as x goes to c of 9 minus x squared, which is 9 minus c squared. And that is exactly what f of c is. Do you see that? Oh, you see. Continuity, we had 3 things have to happen for continuity. We pick the number c. Can you, if c is somewhere in here, can you plug it in? Does it exist? Yes, that was number 1. Can you do the limit as x gets close to c? Yes. Are the limit and the function exactly the same? Yes. So technically, by just showing this part here, you've shown all 3 things. You showed that plugging in c gives me f of c, it exists. Doing the limit exists. And the limit and f of c are exactly the same thing. This is formal. When we talk about it, it seems almost so intuitive right now that it's like, do I really need to show that? Like, again, a lot of stuff you're going to be able to do with just like, yeah, I can see, I can draw it, and I can fill in my endpoints, so it's going to be continuous from A to B. And a lot of math you're going to be fine with just being like, this makes sense to me, okay? In calculus and in math, there's like these weird situations that things get messed up and they get really complicated, and you have to go back to these very simplistic formal definitions to make them work. So one thing I'm going to warn you about university is that the professors in the university have seen those really weird situations, and they're like, I want you to be really formal right from the beginning. You're like, but do I have to? It's like obvious. Okay? So you just humor them a little. Know that they're doing that for a reason, that if you got to those really complicated situations, you'd be ready. But technically at this point, you're okay with being like, yeah, I get it. It's continuous. Okay? So this part would only prove that it's continuous on the open interval. Technically, for any number in the open interval, I should maybe put that there. Then you check the endpoints. And if the limit as you go on the blue arrow here, this is the blue part, as you go from the right to 3, you get to the endpoint. Yes. And here's my purple arrow. If I go to positive 3, there should be a positive in there. Positive 3 from the left side, I get f of positive 3. And everything works out. That's formally how we prove something is continuous on a closed interval. Okay. The exam won't get into too much formal stuff, but they're going to be talking a lot about continuity on open intervals, on closed intervals, how important that is in order to use a theorem. So you're going to be asked to often state, I know it's continuous on a closed interval, before you're allowed to use something new. Okay? The next definition we're going to look at, okay, is something continuous on its domain. In other words, if x is possible, is it continuous where x is possible? So here we have x squared plus 3 over x minus 2. I hope you recognize that there's a non-permissible value at 2. Right? If you graph this, it would be a vertical asymptote at 2. The domain is everything but 2. In other words, if it's going to be continuous on its domain, take each part of its domain. Think of this one with an asymptote. Could you draw the left side without lifting your pencil? Yes. Could you draw the right side of that asymptote without lifting your pencil? Yes. Intuitively then, we will say this is continuous on its domain. Can we say it's continuous? No, because it has an infinite discontinuity in it. So overall, it's not continuous because it has a discontinuity. But it will be continuous wherever it exists. If it exists on a part, can you draw that part without lifting your pencil? Yes. So f is not continuous at 2, but for all the numbers between negative infinity and 2, we can prove using, you could plug in any number in there, and the limit will be exactly, if you can just plug it in, because it's not equal to 2, f of c. This one statement technically proves all 3 conditions of continuous at a point. And since we picked a random point and showed it's true, that implies that it's true for all the points. You didn't, like, it would be really time consuming to do them all. Like start with, okay, negative 5. Yep, negative 5 works. All 3 things for negative 5 work. Then do negative 6. And once you do all the negative whole numbers, you're like, oh, I haven't done any decimals yet. I have to do negative 5.2. And you do negative, oh, and I haven't done negative 5.20003. Individually, there'd be an infinite amount of numbers to try. Mathematically, that's impossible to do. So mathematically, what we do as an idea is we say, I'm just going to pick some random number C and not tell you which one it is. And if I show that it works with the random number C that I picked, and I didn't tell you which one it is, it implies that it works for all of them. And this is like a higher level math way of like cheating. Like, I don't want to do all the points. That would take me forever. So I pick a random point, don't tell you which one it is, just call it C. And if I show that it works for the random point C, that implies that it would work for any point. So this shows that it is continuous for everything from negative infinity to 2. We could do the same thing for 2, right? And it seems, again, really silly in some ways, but we're just applying the definition. All things are, f of c exists, the limit exists, and they're equal to each other. This means something is continuous on its domain. Continuity allows you to do derivatives. Well, technically, we're going to have to add the very complicated math word smooth into this. If a function is smooth and continuous, we'll be able to find its derivative. Can I show you a function that is not continuous on its domain? Just as an added example. Let's say this one goes up to 5 and down to -3, has a hole at 2, 3, but has the point 2, 1. It's a really big 1. I didn't want to write a decimal, but I drew my dot too high. Okay? What is the domain of this function? It includes -3. It includes 5. Does it include every x in between? It does. Even though there's a hole, 2 is allowed. This one is not continuous on its domain because it has, what kind of discontinuity is this one called? Jump, infinite, or removable?
Jump.
It's a removable.
Yeah.
Okay? Because if you just filled in that dot, it would make it continuous. This one would be something that's not continuous on its domain, because there actually exists something at that value where it jumps. But any graph that we've done so far with asymptotes, if it's continuous on the left, it's continuous on the left side of the asymptote, it's continuous on the right side of the asymptote, it's going to be continuous on its domain, but not continuous everywhere. That makes sense. Okay. So here's the graph that we just did. It is continuous on its domain because left of the asymptote you could draw without lifting on its pencil. So that part of its domain, it's continuous. Right of the asymptote you could draw without lifting your pencil. That's continuous on its domain. But it's not continuous on all numbers because there's an infinite discontinuity at x equals 2. This is going to be important later on because we'll want to do derivatives. Very exciting stuff. Really calculus type word. We're going to want to do derivatives of something like this, and we're going to find out we can do the derivative everywhere on its domain. We won't be able to do the derivative at the asymptote. You can only do things, the derivative, where a graph is continuous, and we'll also find out that you can only do derivatives on graphs that are smooth, right? Have no sharp points that if you touch them, your finger would bleed. See how it's nice and round there? It's like, doesn't hurt my finger at all when I touch that. That's the definition of smooth. Some graphs, absolute values, ouch. They have a very sharp point at the bottom. Parabolas are nice. It's like a baby's bottom. Absolute values, that's like a needle. It's sharp point on there. We're going to find out that's not smooth at all. Okay, so with that, all functions we have graphed, some of the piecewise functions, no, are continuous on their domain. Everything you've done so far has had that.